Alright, in this set of notes I'm going to talk specifically about a specific instance when you have a force applied at an angle. Normally in other quote-unquote normal situations, the normal force is equal to the force of gravity, which is the same thing as an object's weight. Okay, and the free body diagram for that would be something like this. For instance, if you're sitting in your chair right now, the force of your weight on the chair equals the normal force of the chair pushing up on you. That's what happens in a normal circumstance. However, there are instances when the normal force is not equal to the force of gravity, and one of those is when a force is applied at an angle. When forces are applied at an angle, there are components of that force that go into the x and the y direction, and that means that you're going to have more than two forces in the y direction, which means things are going to be a little bit different. To explain that, I need to just go on with this problem here. So let's imagine we have this 60-kilogram gazelle. Who knows why it's a gazelle, but it is. And let's actually change this. Instead of pushing on it, I want to pull on it, which means this diagram is going to change. I don't want this, I want this. I want to give it a 200 Newton force at a 60-degree angle. Alright. Force of 200 newtons as shown in the picture. It gives us these numbers, which are the coefficients of friction. That's a dead giveaway that friction is going to be involved. And I actually am not going to do this part. These problems are really similar to what we had with projectiles at angles. And for those, the first step was always to resolve the vector into x and y components. And that's also going to be the first thing that we need to do for these problems as well. So anytime you have a force and an angle, or a velocity and an angle, the first thing you need to do is to resolve the vector into x and y components. And that's done exactly the same way as we did it before. We have a 200 Newton force at a 60-degree angle. There's the x component, and there's the y component. And the little shortcuts that we used to take to find the x and the y components are also still the same. The force in the x direction is found by multiplying the force times the cosine of the angle, f cosine theta. It's f cosine theta now instead of v cosine theta because they gave us a force instead of a velocity. And the y component of the force is found by multiplying the force times the sine of the angle. So what I would put into my calculator for the x component is 200 cosine 60. And for the y component, 200 sine 60. And if you work those out, punch that directly into your calculator, you would find that the x component is 100 newtons and the y component is 173.2. It's also really important at this point that we look at these and ask ourselves a question if these components are positive or negative. X component going to the right, that's a positive direction. Y component going up, that's a negative or positive direction also. Alright, and at this point, just like we did with projectiles at angles, the very next thing we're going to do once we find the x and the y component is to get rid of the original force and angle. Those will not do us any good anymore. We must work things in terms of direct y and x directions in this class. This is in between, so it's not going to help us. Okay. Now I'll come down here and draw the free body diagram. I know that I have the force of gravity. I know I also have a normal force because I'm on a surface. And I have a force of friction. That's a giveaway because of the coefficients. What's really important at this point, and make sure to make a note to yourself, is that don't put any forces at angles on a free body diagram. It's my preference, but I think it works. No forces at angles on the free body diagram. Instead of that, once you resolve these, take the x and the y components and put those in here to your free body diagram. There's your x component, and here is your y component. That's our completed free body diagram. Alright, and many times when you have problems like this, the first question they'll ask you to do is to solve for the normal force. If we look at our free body diagram, the normal force is a force that's in the y direction, in the up and down direction. And you need to know that since this object is sitting on a surface, anytime we have something sitting on a surface, the acceleration in the y direction will be 0, which means the sum of the forces in the y direction will also be 0. That's important to know because I can sum the forces in the y direction. I can add them up. That'll be the normal force plus the y force plus the force of gravity. And those have to add to 0. I know the y force. I just found it. Normal force is what I'm trying to find, but I don't know the force of gravity yet. So I can find that very quickly by doing mass times gravity. The mass of this gazelle is 60 kilograms and gravity is 9.8. So the force of gravity is 588 newtons, and that will be negative when we put it into the equation because the force of gravity goes down, so it should be negative. Normal force plus the y force, which is 173.2, positive, plus the force of gravity, negative 588. Alright, the next step would be to add 588 to both sides, and we get this. And the last thing to do would be to subtract 173.2. We always do the opposite of the operation we're given. And that leaves you with a normal force of 414.8 newtons. Notice something. Before this point, the normal force has been the same as the force of gravity. Compare these two now. They are not the same. Because we're pulling up on the gazelle, there's a component of our force that's going up in the y direction, which means we can take some off of the normal force. Our force itself is sort of helping out the normal force. It's helping to support the gazelle. So the normal force is not quite as much as it would be in a normal circumstance. Now I want to show you how this really isn't that different from what we've done before. Okay, you might be looking at this and saying, well, how did that come into play? Why did we use that sum force equation? Well, we really did before. See, when we had a situation like this, say if you're sitting in a chair, and we found the force of gravity to be negative 588 newtons. We knew intuitively, looking at this free body diagram, that the normal force also has to be 588 newtons because these forces have to be balanced, so that equals that. And what you just did in your head without doing any math was really the same thing, because you knew that since the forces are balanced, that the sum of the forces in the y direction has to be 0. And really this is no different from the sigma F equals ma equation. And we knew that in this case A is 0, which means this whole side goes to 0. So if the sum of forces is 0, we also did the same thing that we normally do on the left side of the equation, which is to flesh it out into the forces that are summed. The normal force plus the force of gravity equals 0. And in our heads, without really doing the math, we knew that the force of gravity was negative 588. We added that to the other side, and that meant that we got positive 588 newtons for the normal force. We did all of that. But you don't have to do all this math because it's really easy to see when you have two forces. Up equals down, down equals up. It's pretty simple. Well, it's still the case with this one that up equals down. these forces had to add together to equal this one force for the sum force to equal 0. But the same thing is that the sum force is still 0. But notice what we got in this step right here. The forces going up equal the force going down. Same concept, but we actually have to write it out now because we have 3 forces instead of 2. Alright, so that's how to find the normal force when you have a force directed at an angle. You sum the forces in the y direction and they'll always add to 0, assuming we're on a surface. Next step, determine if the object will move. Well, if it's going to move, it's not going to move in the y direction, it'll move in the x direction. And the interesting thing about applying a force at an angle is that when that happens, only the x component contributes to the x motion. The y component has nothing to do with it. So if it's going to move, the x component of the force will cause it to move. And for that to happen, we have to overcome this opposite force. This language tells us that the object is initially at rest, in which situation we have static friction. So I need to know what the force of static friction is to figure out if the object will move, because I already know what the x force is. I found it up here at the very beginning. It's 100 newtons. I'll probably go ahead and write that in here. Question is, what's the friction force that I'm fighting? Notice at the beginning they gave us coefficients of friction, and that's a pretty good clue that you're going to use the fun equation, which is this, and this is when we use it. So to find the force of friction, I know that the static friction coefficient they gave me is 0.08 times the normal force I just found of 414.8. And if you multiply those two together, you will get a friction force of about 33.2 newtons. So we can put that in here. So will the object move? Yes, it will move, because the friction force is less than the x force that we're applying. We have an unbalanced force situation here. So we're going to get acceleration. The speed is going to change. It's going to move from 0 to a non-zero speed in this case. So the object will move, which takes us to the next part where they want us to solve for the acceleration. And I'm not going to solve this last part. If you have acceleration, or if they ask you for acceleration, you'll probably be using this sigma f equals ma equation. Now, you might also be thinking, well, acceleration is final velocity minus initial velocity divided by time, which is true. The only problem is they didn't give us any velocities here. So I can't use this equation. Sigma f equals ma is what we're going to go with. Now, on the left side of the equation, we have to write down what forces are going to be added, and those are the forces that are in the direction that we have acceleration. Looking at our free body diagram, I know there's no acceleration in the y direction, so I don't care about those forces for this problem. I'm just looking at the x direction forces, which is going to be the friction force and the x force, and that will equal the mass times the acceleration. The acceleration they ask us to find, that's what we're looking for. I know the mass of the gazelle, I know the x force. I need to know the frictional force as well. Now you might be thinking, well, wait a second, frictional force was 33.2 or 33 newtons. Yes, it was, but that was static friction. If we're going to solve for the acceleration, now that we know the thing is moving, I can assume that it will be moving, it'll be sliding, which means we need to use kinetic friction. So I've got to first calculate the force of kinetic friction by using the same equation. And I can look up here and use my other coefficient now, 0.05. So mu k is 0.05. Normal force hasn't changed. Then if you multiply those together, you'll find a kinetic friction force of 20.7 newtons. And it's really important at this point to look at your free body diagram and note the direction of the frictional force. that it will be negative and should be negative when we put it into our sigma F equation. So negative 20.7 plus the x force of 100 newtons equals the mass times the acceleration. Mass is 60. 100 minus 20.7 gives us 79.3 positive. And if you divide both sides by 60, you'll find that the acceleration is 1.3 meters per second squared. So that's basically how to work a problem involving a force applied at an angle. They will probably ask you the normal force. They'll ask you if the object will move. They may ask you to find what the force of friction is, either static or kinetic. And they could ask you to solve for the acceleration if the object will move. Okay, and the main difference between this and the problems that we worked before with forces and friction is that now instead of 2 forces in the y direction, we actually have 3 in the y direction. Or possibly more for that matter. And the gravitational force is no longer equal to the normal force.